A neutrino is a fermion, an elementary particle with half-integer spin, that interacts only via the weak subatomic force and gravity. The mass of the neutrino is much smaller than that of the other known elementary particles. The neutrino is so named because it is electrically neutral, it is not affected by the electromagnetic force, and because its rest mass is so small, that it was originally thought to be zero. The weak force is a very short-range interaction, gravity is extremely weak on the subatomic scale, and neutrinos, as leptons, do not participate in the strong interaction. Thus, neutrinos typically pass through normal matter unimpeded and undetected. Neutrinos come in three flavors: electron neutrinos, muon neutrinos, micro, and tau neutrinos. Associated with the electron, muon, and tau, respectively. Each neutrino also has a corresponding antiparticle, called an antineutrino, which also has no electric charge and half-integer spin. Neutrinos are produced such that there is no overall change in lepton number. That is, electron neutrinos are produced together with positrons, anti-electrons, and electron antineutrinos are produced with electrons. Neutrinos can be created in several ways, including in certain types of radioactive decay, in nuclear reactions such as those that take place in a star, in nuclear reactors, when cosmic rays hit atoms, and in supernovae. The majority of neutrinos in the vicinity of the Earth are from nuclear reactions in the Sun. About 65 billion, 6.5 times 1010 solar neutrinos per second pass through every square centimeter perpendicular to the direction of the Sun in the region of the Earth. Neutrinos oscillate between different flavors in flight. That is, an electron neutrino produced in a beta decay reaction may arrive in a detector as a muon or tau neutrino. This oscillation requires that the different neutrino flavors have different masses, and although the value of the masses is not known, experiments have shown that these masses are tiny. From cosmological measurements, it has been calculated that the sum of the three neutrino masses must be less than 1/millionth that of the electron. There are several active research areas involving the neutrino. Large neutrino detectors near nuclear reactors or neutrino beams from particle accelerators attempt to measure the neutrino masses and determine the precise values for the magnitude and rates of oscillations between neutrino flavors. These experiments are also searching for the existence of CP violation in the neutrino sector. That is, whether or not the laws of physics treat neutrinos and antineutrinos differently. Many are looking for evidence of a sterile neutrino, a fourth neutrino flavor that does not interact with matter like the three known neutrino flavors. There are also experiments searching for neutrinoless double beta decay, which, if it exists, would require that the neutrino and antineutrino are really the same particle. Then there are solar and cosmic neutrino experiments, which use neutrinos from space to understand the universe around us. Neutrinos are also the only identified candidate for dark matter, specifically hot dark matter.